Hello everyone, my name is Naina and I'm from the Buddhi Academy. So today we'll continue with the part that is structure of atom, and in today's video we'll see about the Bohr's model of hydrogen atom and what are the limitations of Bohr's model. So Niels Bohr was the first to explain the quantitatively the general features of hydrogen atom structure and its spectrum. So Bohr was the person who explained the structure, features and structures of hydrogen atom and its spectrum also. So though the theory is not the modern quantum mechanics, it can still be used to rationalize many points in the atomic structure and spectrum. So it is not the one which is we follow now, that is the modern one which we follow, but it can explain certain points of the atomic structure and spectra. Okay, Bohr's model for hydrogen atom is based on the following postulates. So Bohr's model, it is basically on the following postulates, and they are: first one is the electrons in the hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. These paths are called orbits. So as I told you, it is said that electrons in hydrogen atom, they can move around the nucleus in a circular path. So if this is a nucleus, around the nucleus, the electrons can move in a circular path, and this path is known as orbit. Okay, stationary states are allowed energy states. Okay, this is known as orbit. Mostly we call them as orbits now. So orbits, stationary states are allowed energy states. Okay, so these orbits are arranged concentrically around the nucleus. Concentrically means if this is a nucleus, it is like this. The center will be same, but the size will go on increasing. So like this, the orbits are arranged around the nucleus. The second point is what? The energy of an electron in the orbit does not change with time. So the energy of electron, whichever electron is present in this orbit, the energy of this electron, it doesn't change with time. So as time goes, this energy is not removed or doesn't loses any energy. So the energy change is not observed. However, the electron will move from a lower stationary state to a higher stationary state when required amount of energy is absorbed by the electron or energy is emitted when electrons move from higher stationary state to lower stationary state. So the energy, it doesn't changes over time, but when an electron absorbs energy, it can move from its lower energy state to a higher energy state. Okay, and the electron when electron emits the energy, when energy is given out, it comes from its higher energy state to a lower energy state. So this is when energy is given out, and this is when energy is taken in. So when energy is taken in, the electrons move from their lower energy level to a higher energy level. And whereas when electron, it emits the energy, it comes from its higher energy level to a lower energy level. Okay? So the energy change does not take place in a continuous manner. It doesn't go on like this, going up, coming down, going up, coming down. It is not a continuous manner. Okay. What is an angular momentum? Just a linear momentum is the product, just as linear momentum is the product of mass and linear velocity. Angular momentum is the product of moment of inertia and angular velocity. So it is something with angular velocity. For an electron of mass me moving in a circular path of radius r around the nucleus, angular momentum, it is equal to I, that is inertia, and omega, that is angular velocity. Okay. Since I is inertia is me by r square, and omega, that is your angular velocity, is v by r, where v is linear velocity, r is the radius of the path. So angular momentum is equal to me VR. So this is the angular momentum. We can use this in the calculation of various problems. Okay. Now, third point is what? The frequency of radiation absorbed or emitted when transition occurs between two stationary states that differ in the energy by delta E. So as I told you, whenever the electron, it absorbs or emits energy, whenever it takes or it gives out energy, there is a transition, right? It moves from a lower energy level to higher energy level, or vice versa, higher to a lower energy level. So in both the cases, there is a difference in energy, and that difference in energy is given by delta E. So V equals delta E by H, where delta E is E2 minus E1. E2 minus E1, it can either be a, if it is uh, if the electron is emitting the energy, it is giving out the energy. So in that case, the electron will move from a higher energy level to a lower energy level, right? In that case, it will be E2 minus E1. That is, this one is E2, this energy level is E1. So it is E2 minus E1 divided by H. Okay. So where E1 and E2 are the energies of the lower and higher allowed energy states respectively. So it is the energy levels. Okay. So this expression is commonly known as Bohr frequency rule. So it is known as Bohr's frequency rule. So that is V is equal to delta E by H, which is equal to E2 minus is E2 minus E1 divided by H. So this formula, this is known as Bohr's frequency rule. Okay. So fourth point, the angular momentum of an electron in a given stationary state can be expressed in this equation. So when the momentum is stationary in a given stationary state, that is your orbit, okay, it is given as, so what is angular momentum? As I told you, it is MEVR, right? It is MEVR is equal to n dot h by 2 pi, where n can be 1, 2, 3, anything. Thus, an electron can move only in those orbits for which its angular momentum is integral multiple of h by 2 pi. Okay, that is why only certain fixed orbits are allowed. So it should be an integral multiple of h by 2 pi. That's why only certain fixed orbits are allowed. So the details regarding the derivations of energy of stationary states used by Bohr are quite complicated and will be discussed in higher classes. So there are derivations regarding how this stationary states, energy states are used by Bohr. You will be learning it in your higher classes as it is a little complicated part. So according to Bohr's theory for hydrogen atom, now let's see how it is for hydrogen atom according to Bohr's theory. So the stationary states for electrons are numbered as n is equal to 1, 2, 3. So this is how the stationary states are numbered. So this is the integral numbers. These are all integral numbers. So are known as principal quantum numbers. So these numbers are known as principal quantum numbers. Okay. The stationary states for electrons are numbered. Okay, all the stationary states for electrons, they are numbered, right? All the orbits, they are numbered. So these numbers are 1, 2, 3, and so on. So these are integral numbers, and these are known as principal quantum numbers. Okay, that is the first point. Second point, the radii of the stationary states are expressed in, now how the radii is expressed is, it is expressed in Rn equals to n square a naught. Okay, now what is A naught? A naught is 52.9 pm. Thus, the radius of the first stationary state is called Bohr orbit. So, the radius of first orbit, first stationary state, that is, this is nucleus, this is the first stationary state, and the radius of this state is known as Bohr orbit. Okay, thus the radius of the first stationary state called the Bohr orbit is 52.9 9 p.m. Okay, so the radius of the first stationary state, that is this, and this state is known as Bohr's orbit. Okay, this is Bohr orbit, and its radius is 52.9 pm. Okay, so normally the electron in the hydrogen atom is found in this orbit. So the electron, as you know that hydrogen has only one electron, right? So the electron in hydrogen atom is found in this orbit, that is Bohr orbit, which is n is equal to 1. So as n increases, the value of r will increase. In other words, the electron will be present away from the nucleus. So as you all know that as the number increases, there will be increase in the orbits also, right? Because all the electrons can't fit in this one small orbit. So there will be various orbits. So as the number of orbit increases, they will be going further away from the nucleus, right? They will go away from the nucleus. So in that case, the radius will also increase, right? The radius of this orbit will be different. The radius of this orbit will be different. So as the number of electron increases, the orbits will also increase, and thus the radius of the orbits will also increase. In other words, the electron will be present away from the nucleus. Okay, that is the second point. The third point is the most important property associated with the electron is the energy of its stationary state. So the most important property is that electrons, wherever the electron is present, is the energy of its stationary state. So if the electron is present here, so it is the energy of this state, electrons in their stationary state. So it is given by the expression En RH multiplied by En equals minus RH multiplied by 1 by n to n. You know it is 1, 2, 3. So it is the integral numbers or the principal quantum number. So where RH is called as Rydberg constant. So it is the Rydberg constant, and the value is 2.18 into 10 raised to minus 18 joules. So where RH is the Rydberg constant, and the constant is also given here, that is 2.18 into 10 raised to minus 18 joules. So the energy of the lowest state, also called as the ground state. So the energy of the lowest state, I told you, there is lower energy level, higher energy level. So the lower energy level, it is known as ground state. Okay, and the energy of this ground state is E1. Now it is the ground state, right? So it will be E1, first one, right? So E1 is equal to RH value, we know that is 2 point minus RH ka value 2.18 into 10 raised to minus 18. Now 1 divided by n square. N square means now it is the ground state at first energy level. So it will be 1 square. So the energy level, okay, the energy of the lowest state or the ground state is minus 2.18 into 10 raised to minus 18 joules. So the energy of the stationary state for N2, similarly you have to calculate, where you have, in place of 1 square we will use 2 square. Okay. So these are the energy levels. Now, this is what they were talking about. This diagram, this structure, it is known as the energy level diagram. As I told you, this is known as energy level diagram, where all the energy levels of hydrogen atoms is shown in the stationary state. Okay. So this is where N1, when N is equal to 1. Okay, this is how it will look, and this is the Lehman series. Okay, when n is equal to 2, it is a visible part, right? This entire part is the visible range. So this is Balmer series. Okay, and when n is equal to 3, 4, 5, 6, infinity, these are Paschen series. Okay, there are other series also. Okay, apart from Paschen, there is bracket and Pfund series also, but here only till Paschen series is shown. Okay, this is of hydrogen atom. This is the energy level diagram of hydrogen atom. Okay. So when electron is free from the influence of nucleus, okay, the energy is taken as zero. Now, why there is an influence between free electrons and nucleus? Nucleus contains protons, and protons are positively charged. Electrons are negatively charged. So they are oppositely charged atoms, electrons, right? Molecules. So they will pull each other. Like they are unlike charges. They will attract each other. So when the electron is free from the influence of nucleus, the energy is zero. So the electron in this situation is associated with the stationary state of principal quantum number, where n is equal to infinity. Okay, that's why n is equal to infinity, because it is going further and further away from the nucleus. And it is called the ionized hydrogen atom. And those electrons which are not under the influence of nucleus and are further and further away from it, where n is equal to infinity, those are known as ionized hydrogen atom. When the electron is attracted by the nucleus and is present in the orbit n, the energy is emitted and energy is lowered. Okay, so whenever the electron it is attracted by the nucleus and is present in the orbit n, any of the orbit, like 1, 2, 3, any of the orbit, that's why it is n, the energy is emitted. Okay, and its energy is lowered. So energy emitted means obviously it is giving out, so the energy will decrease, right? So that is the reason for the presence of negative sign in the equation. So that's why you can see the negative sign here. This negative sign, okay? This negative sign, it is because it is losing energy, okay? So that is the reason for the presence of negative sign in the equation, and depicts its stability relative to the reference state of zero energy and n equals to infinity. Okay. Now, fourth point is what? Bohr, Bohr's theory can also be applied to the ions containing only one electron, right? Hydrogen, it contains only one electron, right? So Bohr's theory, it can be applied to ions containing one electron, similar to the similar to that present in the hydrogen atom, right? Hydrogen atom contains only one electron. For example, helium plus. Helium plus means what? Helium has how many electrons? It has two electrons. When I remove one electron, it will be He plus, right? Lithium 2 plus. Lithium 2 plus means what? Lithium, it has three electrons. I'm removing two electrons. So it is Li2 plus. It requires two electrons, right? 3 beryllium 3 plus, that means only one electron is left with all these three molecules, right? So it can explain the structure theory. This theory can also be applied to these molecules, and all these three molecules has only one electron, similar to hydrogen atom, right? So the energies of the stationary states associated with these kinds of ions, also known as hydrogen like species. So these are known as hydrogen like species because they all contains one electrons, similar to hydrogen atom, are given by the expression. So for these hydrogen like species, to calculate their stationary state, okay, the expression given is this, that is En equals to minus 2.18 into 10 raised to minus 8. This is the Rydberg constant, multiplied by z square upon n square J. J is the unit, it is joules. So, and radii by the expression. So, this is how you can calculate its energies level. Okay, stationary states energy level, all the energy levels associated with it. Now, how you will calculate radius? It is calculated by this formula, where Rn, that is radius, n can be What can be n? 1, 2, 3, so on. So this will be n. So Rn is equal to 52.9 n square upon z. Now what is 52.9? It is the radius of Bohr's orbit, right? Where z is the atomic number. Now everywhere you find that it is using z, right? Z square divided by z. So z is the atomic number of all these molecules, whichever is like hydrogen-like species, no? Their atomic number is used in this calculation. That is the z square or z. So z is the atomic number and has a values 2, 3. Like for helium it is 2, like, and for lithium it is 3 atoms respectively. So from the above equation, it is evident that the value of energy becomes more negative and that of radius becomes smaller with increase of atomic number. Okay, so the radius becomes smaller with the increase of. So it is evident that the value of energy becomes more negative and that of the radius becomes smaller because all these atoms are removing electrons to look like a hydrogen like species, right? So their size will also, so the radius becomes smaller with increasing z. So this means that electrons will be tightly bound to the nucleus. So they will be tightly held by the nucleus, right? Then it is also possible to calculate the velocity of electrons moving in these orbits. So you can also calculate the velocity of the electrons moving in those orbits. Although the precise equation is not given here, qualitatively the magnitude of velocity of electrons increases with increase in positive charge of the nucleus and decrease with the increase in principal quantum number. Although to calculate, the formula is not given here, it is said that the magnitude of velocity of electron, it increases with the increase of positive charge on the nucleus. So as you increase the protons, the velocity will also increase. The magnitude of velocity of electrons will increase as the positivity of the nucleus increases and decrease with the increasing of principal quantum number, that is the n. When n decreases, at that time we can calculate the velocity or magnitude of the velocity of electrons. Explanation of line spectrum of hydrogen. Now, what is the line spectrum of hydrogen? Okay, line spectrum observed in case of hydrogen atom can be explained quantitatively using Bohr's model. Okay, so the line spectrum, it can be quantitatively explained using Bohr's model. According to assumption 2, radiation, that is energy, is absorbed if the electron moves from the orbit of smaller principal quantum number to the orbit of higher principal quantum number. So it is seen that the energy is absorbed if the electron moves from the orbit of smaller principal quantum number. That is, if I have a orbits, okay, this is 1, 2 and 3. So it is observed that whenever an electron, it is absorbing an energy or radiations, it is seen that this electron, it moves from the lower principal quantum number to a higher principal quantum number. That is, it is moving from 1 to 2. Okay. Whereas the radiation or energy is emitted if the electron moves from the higher energy orbital to lower orbital. So it is the vice versa, as I told you. Whenever it absorbs an energy, it will go from the lower to higher part, and whenever it is losing energy, it will go from the higher to a lower part. Okay, so the energy gap between the two orbits is given by, so there should be a gap between the orbits, right? And this gap is given by delta E is equal to EF minus EI. So where EF is the final electronic level, EI is the initial electronic state. So where the initial energy level and the final energy level. So combining both these equations, okay, that is combining this equation, that is En is equal to minus RH upon 1 by n square, and this equation, what we get is, so whereas N1, Ni and Nf, so we'll use Ni and Nf in place of N1 and N2. So it will be RH. So just combine both the equations. This one will be for EF and this one will be for EI. Delta E means EF minus EI. So what is EF? It will be RH, that is minus RH, minus 1 upon NF square, because it is N1 square. So this is for EF. Similar will be for EI. So when you combine both of them, it will be like this. RH will come common, right? So 1 by Ni square minus 1 by Nf square, it will be remaining in the bracket. Now, RH is the Rydberg constant. So this is the Rydberg constant, right? So this is how you will use to calculate the energy gap of the orbits. So the frequency associated with the absorption and emission of the photon can be evaluated. Now how you will evaluate the frequency? So it can also be evaluated using the same formula, where RH is the Rydberg constant, H is the Planck's constant. So both the constant values you know, this you will get by the energy levels. So you can calculate the frequency associated with the emission or absorption of the photon. Okay. Now, in short, if I calculate both these quantities, that is the RH by H, the value comes something around 3.29 into 10 raised to 15. So this is the value of RH by H. Rydberg constant divided by Planck's constant. We get value something around 3.29 into 10 raised to 15. So this is how you can calculate the frequency. Okay. Now, in terms of wave numbers, how you will calculate the wave number? So, wave number is equal to frequency by C. Frequency is RH by H, that is Rydberg's constant. C is the speed of light. So, RH by H, that is Rydberg constant divided by Planck constant. We know the value is 3.29. So, 3.29 into 10 raised to 15 seconds per seconds divided by what is the value of speed of light? Speed of light is 3 into 10 raised to 8 meters per second. Okay. So that will come around 1.09677 into 10 raised to 7. The this is how you can calculate the wave number. Okay, now how you know how to calculate delta E, frequency, and the wave number. So in case of absorption spectra, NF, that is, so NF is the final state, energy state. So it is greater than the initial energy state. Because why it is greater? Because you are moving from a lower energy level to higher energy level in the absorption spectra, right? Whenever a electron absorbs energy, it will move from a lower to higher. That's why final one will be greater than the initial one. Okay. And in terms of parenthesis is positive and energy is absorbed. So in this case energy is absorbed, so it will be positive. Okay. In other hand, in case of emission spectra initial will be greater, right? Because it is coming from the higher to a lower energy level. So initial will be greater than final. So in this case, delta E will be negative and energy is released. Okay. So in absorption spectra, delta E will be positive because you are moving from a lower level to a higher level, right? And in case of emission spectra, it will be negative as you are coming from a higher level to a lower level. So the expression is similar to that used by Rydberg, derived empirically using the experimental data available at that time. So this is what Rydberg has derived using his experimental data available at that time when he was there. So each spectral line, whether in absorption or emission spectra, can be associated to the particular transition in hydrogen atom. So each of the line spectra, whether it is an absorption or emission, can be associated with particular transition in hydrogen atom. So in case of large number of hydrogen atoms, different possible transition can be observed and thus leading to a large number of spectral lines. So if there is more number of hydrogen atoms, you can see different possible transition that can be going up, going down. There can be hydrogen atoms which is moving from one energy level to another energy level. So there can be various lines that can be observed, which is leading to the large number of spectral lines. So brightness or intensity of spectral line depends upon the number of photons of same wavelength or frequency absorbed or emitted. So its brightness or intensity, it is basically depending upon the number of photons of same wavelength or frequency which is absorbed or emitted. Now, limitations of Bohr's model. Why this Bohr's model was later not accepted? What are the limitations? So Bohr's model of hydrogen atom was no doubt an improvement over Rutherford's nuclear model, right? So Bohr gave much more information. He gave more information compared to Rutherford's nuclear model, as it could account for the stability of line spectra of hydrogen atom and hydrogen-like species or ions, right? So he explained much more than what Rutherford can explain. However, Bohr's model was too simple to account for the following points. So because of these following points, his model was not accepted. So first one is it fails to account for the finer details, that is doublet, that is too closely spaced lines of the hydrogen atom observed by using sophisticated spectroscopic technique. Now, it wasn't able to explain the finer details. Finer details means there is a doublet. There is two lines close between each other. So like this, there are two lines which are too close with each other of the hydrogen spectra, which is observed by using a sophisticated, more high-tech spectroscopic technique. So this model is also unable to explain the spectrum of atoms other than hydrogen. So according to Bohr's theory, according to Bohr, it can explain the hydrogen atoms, right? But it could not explain the spectrum of other atoms like helium atom, which possesses only two electrons. So further, Bohr's theory was also unable to explain the splitting spectral lines in the presence of magnetic field, that is Zeeman effect, and or electric field, that is Stark effect. So Bohr's model in general, it can explain the hydrogen atoms line, spectral lines. But when the spectral lines are under magnetic effect or an electric effect, the lines will split. So that splitting of spectral lines was not able to explain by the Bohr's theory. Okay. And second, it could not explain the ability to add of atoms to form molecules by chemical bonds. So this is the basic one, that it could not explain the chemical bond formations because it is necessary to form a chemical bond, to form a molecule, right? So Bohr's theory, it wasn't able to explain this chemical bonds. So in other words, taking into account the points mentioned above, one needs a better theory which can explain the salient features of the structure of complex atoms. So there should be more to explain the complex structure of atoms. So this led to the quantum mechanical model of atom. So in our next class or next video, we'll see about the quantum mechanical model of an atom. So in today's class, we have seen about the Bohr's model. We have also seen about their energy levels, how the hydrogen spectrum lines are there, how to calculate all those values, then limitations of Bohr's model. So thank you for watching my video. Please do like, share and subscribe to our channel.